Assalamu alaikum everyone. So today we will be having our 16th lecture, right? And we will be discussing a little bit about multiplexers, then encoders and decoders, right? So let's start. So these are the bullets which we will be going through one by one. First we will finish multiplexers, then we will talk about decoders and encoders and their utilization, right? So we can use a multiplexer as a combination module, right? For example, if we have 3 input, right? So we can have 2 input as we can select 2 inputs as a control switch, right? So over here you can see we have 3 inputs, right? And XYZ, and we have chosen 2 of the inputs as control switches or control inputs, right? So in this way, in total we will have 2 raised to power 3, 8 different combinations. So as we have chosen 2 of the inputs as the control switches, so we are left with only 4 inputs, right? So 4 into 1 multiplexers, and you can see we have in the truth table XYZ, we started from 0, 0, 0, and then you can see that we have in the output in pairs, right? So here we have F01, right? F is equal to Z, right? And then we have F is equal to Z bar. So you can see that F is always the Z. So here F is Z bar. You can see we have the complement of Z, right? So this is also paired, and then we have on this input combination 1 0 0, right, or 1 0 1, we have 0 0, right? So here we have 0 0, right? And then we have F is equal to 1, right, when we have this combination starting from 1 1 0 and then 1 1 1, we have all time 1, right? So you can see that we have here the control is repeated 0 0 if we talk about 0 0, right? 0 1 1 0 1 1, right? So this is a sort of combinational use as a combination multiplexer use as a combinational module, right? So here we have increased the number of variables, right? A, B, C, D, right? We have 4 inputs over here. So in normal we must have, or we should have 2 raised to power 4, 16 different inputs, but as we have chosen 3 of the inputs as control inputs or control switches, so we will left only with 8 input combinations, right? So if you talk about the control switches, so you can see that A, B, C, they are connected with S0, S1 and S2 respectively, right? And you can see that we started from this combination 0 0 0 0 and till we reached 1 1 1, right? So total 16 different combinations starting from 0 to 15, right? So you can see that we have pairs here. So you can see that F is D, right? So on those 2 combinations, right? So F is D. Then here again we have F is equal to D, right? And this is also a pair of combinations, and again here you have F is equal to D complement, right? F0, right, on those 2 inputs, and then again F0, F is equal to D, F is equal to 1, F is equal to 1. So if we focus on the inputs and we talk about A, B, C only, so you can see that 0 0 0, 0 0 0, so they are repeating. So it means if I count those pairs, so 1 2 3 4 5 6 7 8, right? So that's why I call it 8 into 1 multiplexer. One of the input combination is selected, right, on the basis of S0, S1, S3, right? So you can see that we have 0 0 0 here, 0 0 1, 0 1 0, and so on and so forth till we reach 1 1 1, right? So this is the implementation of a 4 input multiplexer, right? And this is the typical utilization of a multiplexer, right? So you can see that we have different inputs, right? And we can select the multiplexer, either we can select A or we can select B, right? So here this is the control unit or functional unit that has to be controlled or that functions on the basis of these multiplexers, right? So here you can see that this is the output, and output is a function of the input. So here if you look at this block, right, so you can see we have inputs A and B, right, that are basically the output of the multiplexers A and B respectively, and the output is a function of the input A and B, right? And here you can see the output is a function of inputs, right? If you talk about this, right, so if I call this whole circuit as a box, so these are the inputs, right, and this is the output. So the output as a function of input, right? So here we can see that this is the output, right, and these are the inputs R's, right? So output is a function of input, right? So let's talk about decoder, right? So a decoder is actually a logic circuitry that can accept inputs, right? And on the basis of this input selection, it activates only the output that corresponds to that input number, right? So it determines which binary number is present at the input, right? And then on the basis of that input combination, right, it activates one of the corresponding output, right? So if we have a decoder that has n inputs, right, so we can have 2 raised to power n output lines, right? So we will be only activating one input output at a time, right? So if you talk about the example, AND gate is the best example, right? So whenever we have both inputs high, the output is high, right? So this is the best example of a decoder, right? So here we have the block diagram of a decoder, right? So you can see we have n input lines and the output 2 raised to power n, right? So one of the input, right, on the basis of one of the inputs, right, we will be only selecting one output from 2 raised to power n outputs, right? So this is the example of decoder, right, or the use of a decoder. So whenever we talk about the different operations within a computer, so we can have an addition operation, subtraction, right, and we can also have some logical operations, and or not, right, or the data has to be loaded, right, and it has to be stored, and then we can also have a jump condition, right? Whenever we talk about a jump within a programming language or in the context of the computer, right, so we have to jump from one area in the memory into another area within the memory, right, if you are working sequentially, right? So you can have a jump, right? So here you can see that on the basis of those different operations, we have different operational codes, and those operational codes, they are being generated, right, on the by using the decoder, right? So we have op 0, operation 1 and 2, right? So this is a 3 into 8 decoder. So because we have 3 different ops, right, so we can control, or we can represent or activate 2 raised to power 3 8 different operations, right? So here on the right hand side of your picture we have another example, right? So here we have a 2 into 4 decoder, right? And we have two inputs, so 2 raised to power 2, 4 output, and we can control a light, right, an air condition, a door, and a light with AC, right? So 2 raised to power 2, 4 output. So one of the output will be activated at a time, right? So here, if you talk about the truth table, right? So if you have 2 into 4 decoder, so 2 inputs, A0, A1 and A0, starting from 0, 0, and we have 0, 1, 1, 0, and 1, 1, and the output are D0, D1, D2, D3, right? So if we have 0, 0, so you can see D0 is activated, or it has a high. If we have 0, 1, D1 is activated, right? So we have a 1 at D1. 1, 0, D2 is activated, right? All other are 0, and on 1, 1, D3 is activated. So you can see that we have a diagonal, right? So here, if you talk about this diagonal, right? So we have all ones lying onto this diagonal, right? So this is the circuitry, right? So if we talk about the design of the circuit from this truth table, because we already studied that if we have a truth table, we can draw the circuit from that truth table by using minterms. So if I talk about the D0, right? So you can see that D0 will be equal to, right, A1 bar, A0 bar, right? If I talk about D1, right, so we have 1 here only, right? So I will be having A1 bar, right, and A0, right? And similarly we have D2 is equal to A1 A0 bar, right? And D3 is equal to what, right? A1 A0, right? So we can have all the Boolean functions, right? And you can see that these are the inputs, A0, A1, and we have built the circuitry, right? So this is the circuit diagram. You can see D0, D1, D2, and D3, right? So whenever we have D0, A0, A1, 1, 1, right? So you can see only D3 will be activated, all other will be deactivated or will be having 0, right? So we will be having 0, 0, 0, 1, right? So here we have introduced another input, that is enable, and the purpose of this addition is to have more control, right? So you can see that we have 0. This is don't care condition, don't care condition. Whenever enable is 0, so we will be having all zeros irrespective of the input, right? So whatever the input is, right, we always will be having 0, 0 at all these, right? So here if enable is 1, and then we start from 0, 0, right? So D0 is 1. On 0, 1, right, we have the same set of output, and you can see we will be having all ones at this diagonal, right? So this is the 2 into 4 decoder with enable input, right? So you can see the change in the circuitry. If you go back, right, you can see here we have one stage, right? If so you can see you can say that this is one stage, right, one level circuit, right? So if you talk about this, right, decoder with enable, so you can see we have two stages, right? For in the first stage we have if we have the circuit without enable, right, this is the same, we have here, and look here, we have the circuit for 2x4 decoder, right? And we can say it one stage circuit. We have only one level, right? AND gates, right? And if we talk about this 2x4 decoder with enable, right? So you can see the addition of one more level due to this enable, right? So this circuitry is the same as we have before, but to have more control, we need to add one more level of AND gates, right? So here we have enable, and this enable is connected with the output of this decoder, right, via an AND gate, right? So here you can see we have the 2x4 decoder with an enable, right? So this is another decoder, right? So here we have the same truth table, right? 2 input. So we normally have 2 raised to power 4 output, and one of the combination will be activated at a time, right? So 0 1, so this combination will be activated, right? So here we have 3 into 8, or you can say binary into an octal binary decoder, right? So here x, y, z, so we start from 0 0 0 and we go on till we reach 1 1 1, right? So you can see here we have f0 high, all other are 0, right? So here we have f1 high, right? So then we have f2 high, right? f3 high. So you can see we have the corresponding bits high, and if you talk about the diagonal, so we have this diagonal, right? All ones onto this diagonal, right? So this is a typical 3 into 8 decoder, right? So 3 inputs, so one of the combination will be activated, right? So here if we talk about, so f7 is high, all other are 0. So this is the circuitry. We can always build the circuitry from the truth table. So here for f0 you can see we have only 1, right? All other are 0. So we have x bar, y bar, z bar. So this is the f0. If you talk about f1, right? So here we have 1, right? So we will be having x bar, y bar, z. So x bar, y bar, z, right? If you talk about the f7, we have x, y, z, right? So here you can see these are the 3 inputs, right? And these are the 4 2 raised to power 3 8 output, right? So only one of the output will be activated on the basis of the input combination, right? And if we talk about the decoders, we can have a parallel decoder, right, and a normal decoder. So here you can see that we have the parallel decoder, right? You can see they are parallel, right? So here we have the complemented, right, output m0. This is complemented here, m1, right here, m1 is complemented here. So this is, if you talk about least significant bit and most significant bit, so we will talk about. So here m0 is equal to a bar, b bar, right? And the problem with the parallel decoders are they are a bit expensive, right? And if we have to extend, for example, if we have for example 3 input decoder, right? So you have to increase 3 to 4, right? So the circuit will be more complex, right? So 2 raised to power n decoder require n input, right, and gates, right? So it means the fan in will be rising, right? So this is the alternate structure. You can see we have cascaded the NAND gates in such a way, right, that here we have 1 2 3 4. If we need to add, we can add easily, right? And it will be less expensive than the parallel decoder, right? So we can always expand our decoder. So if we look here, right, so we have a 2 input decoder till here, right? And if I want to expand this decoder to a 3 input decoder, so you can see the expense of expansion, right? So this is a sort of parallel structure, right? And you can see the number of gates, more gates we have to use if we raise n by 1. So 2 plus 1, and right? So here you can see we have A2, this is the third input, right? And we need 1 2 3 4 5 6 7 8, right? So you need 8 more AND gates if you want to extend this, right? Because sometimes you don't want to redesign starting from the scratch, right? So you want to extend. So the expansion is costly in case of parallel decoders, right? As we have mentioned here, that parallel decoders are expensive if we talk about the expansion, right? So here you can see we have A2, A1, A0 starting from 0 0 0 till we reach 1 1 1, right? So this is the expansion of a decoder. Then we can always implement decoders, right? So this is the implementation of a decoder, right? So here you can see we have a sum, right, or a carry. So it means we have implemented a full adder by using a 3 into 8 decoder, right? So here you can see we have the min terms, right? 1 2 4 7, right? So this is for sum. So 0. If I write here, right, so this is M0, this is M1, this is M2, M3, M4, M5, M6 and M7, right? So you can see we have 1 2 4 7, right? So for sum 1 2 4 7, right? For carry we have 3 5 6 7, right? So you can see we have 3 into 8 decoder, right? So it means we have 3 inputs, right? So these are the control switches starting from S0, S1, S3, right? So here you can see we are not utilizing 0, so the sum will be odd, right? And odd for 1, right, 2, 4 and 7, right? And then we have another OR gate, right? So the input are 3, 5, 6 and 7. This is for carry. So this is the implementation of a full adder by using a decoder, right? So you can have the idea that how we can use decoder, right? So we can now have an adder, right? So this is another implementation of a decoder circuit, right? So here we have a 4 into 16 decoder. So you can see we have 4 inputs and 16 output, right? So on the basis of those 4 inputs, only one of the combination will be activated, right? So you can see that A, B, C, D, right? And if we have to connect those inputs, right, that are mentioned here externally, we have to connect them with the internal control switches. So you can see that we have reversed the order, right? So here D is connected to S0, right? So and C is connected to S1. So there is a a reverse order. So you can see we have the Boolean expression for F1, right? And you can also calculate the Boolean expression for F2 and F3, right? So this is the IC that normally we use for a decoder, right? So you can see we have the schematic, right? The circuitry for this IC, right? And this is the pin configuration, right? All inputs are labeled, right? So these are the select inputs, these are the enable inputs, right? This is the output, ground, and so on and so forth, and these are the data output, right? So this is the truth table, or you can call it a function table. And here we have designed a decoder by using NAND gates, right? So you can see that we have a 2 into 4 decoder, but here we have only used NAND gates, right? So you can see we have the enable. When an enable is 1, right? So irrespective of the input combination, we have all ones, right? Because we are using NAND gate, so now we will be having the diagonal zeros, right? All zeros at the diagonal, right? And this is active low, because when enable will be 0, our circuit will function according to our design, right? So if E0, so we have 0 0, and you can see 0 at D naught, all other D's are 1, right? So 0 0 1, so you can see a 0 at D1, all other D's are 1. So here 1 1, right? All these are 1, and D3 is 0, right? So this is the 2 into 4 decoder, but by using NAND gates, and we have used over here active low, right? So here we can also cascade 2 decoders, right? So here we have 3 into 8 decoders, right? And we have cascaded them in order to have 4 into 16 decoder, right? So if you look here, right? So here we have XYZ, right? This is these are the 3 inputs, right? And from starting from D0 till D7, we have 8 outputs, right? So 3 into 8 decoder, binary into octal, you can say. And we have enable here, right? And this is the other decoder that is cascaded. So 3 into 8 decoder, so same inputs, right? Enable. And the output will be labeled starting from D8 till D7, 15, right? So whenever we have W0, right? So it means this will be high, so this decoder will be selected, right? And whenever we have W is equal to 1, so we will be having a 0 here and 1 here, so this decoder at the bottom will be selected, right? So this is the cascading of decoders. So we have joined or connected 3 into 8 decoders in order to have a 4 into 16 decoder, right? So these are the applications of decoder circuitry, right? So you can see whenever we talk about the I/O ports within or at the input output of a computer, right? So we need to send and receive data, right? So for that you need to activate the port, right? So a decoder can be used in order to activate the input or output port, right? So this is the one of the utilization of the decoder circuitry. We have already seen the utilization of a decoder as a full adder, right? So let's move to encoders, right? So if you look here, right, I call this output as input, right? I, and this input as output, right? Name it or call it O, right? So if you look here, right, so on the input we have n number of inputs, and we will be having 2 raised to power n output, and on the basis of those different n input combinations, right, one of the output combination will be active at a time, right? Only one output will be activated on the basis of the input combination, right? So I'm talking from here to here, right? And this is what? This is the functionality of a decoder, right? If I move in the opposite direction, right, so here you can see we have more inputs and 2 raised to power n inputs and n outputs, right? So it means we have fewer outputs as compared to the number of inputs, right? So this is the functionality of an encoder, right? So this is the opposite to a decoder, right? So here you can see we have 2 raised to power n inputs, right, and we will be having n output, right? So this is the same that in encoding we have the opposite of a decoding, right? 2 raised to power n inputs, right, and n outputs, right? So let's talk about 8 into 3 encoder, right? So here you can see we have, or you can call it an octal to a binary encoder, right? So we start from D0 till D7, and these are the 3 output starting from A0, A1 and A2, right? So we will be having 2 raised to power 3, 8 input, 3 output. Okay, so this is the truth table, right? So if you look here, D3, D6, D5 till D0, and these are the output, right? So you can see we start from 0, 0, 0, 1, right? And this is D1 is 1, right? Here D2 is 1, right? D3 is 1, right? D4 is 1, and so on and so forth till we have 1 at D7 position, right? Or D7 column. So these are the output, right? So here you can see that we have output. So this is 0, 0 starting from 0, 0, 0, right? And 0, 0, 1, this is 1, 2, 3, 4, 5, 6, 7, right? So this is a normal octal to binary encoder, right? So you can see we have 1 at D0, right? 1 at D1, so D7, so we start from 0 to 7, right? So this is the combination, right? So 2 raised to power n inputs and n output, right? So you can see that we have, and then we have the other combination, right? 0, 1, right? And this is another combination, you can see 0, 0 and 1 at D5, right? And we will be having 5, 4 plus 0 plus 1, 5, right? And this is the last combination, right? So 1, 0, 0, and this is, you can see D7, so 4 plus 2 plus 1, right? 7. If you want to compute the Boolean expression, so we will writing the min terms. So if we start from A0, right? So you can see we have D1, right? D3, right? D5 and then D7, right? And then if you talk about A1, right? So you can see D2, D3, D6 and D7, right? And finally we have to compute or calculate the Boolean expression for A2. So this is D4, D5, D6 and D7, but there is some problem, right? And this is the circuitry, right? If you go back, So these are the expressions, right? A naught, right? You can see for A naught we have D1, D3, D5, D7, they are odd, right? For A1 we have D2, D3, D6, D7, they are odd. For A2 we have D4, D5, D6, D7 odd, right? So there is some problem, right? There are some limitations. You can say that whenever we have two ones simultaneously at D3 and D6, right? So it must represent, right? So if so here 1 1 1, right? So it must represent, or you can say it is representing. So if you talk about the 3, right? So we will be having 0, right? So let me write down here. So for 3, D3, we will be having 0 1 1. For D6 we will be having 1 1 0, right? But if we have both D3 and D6 high, right? So it neither represent a 3 nor it represent a 6. So this is problem number 1. And then there is another limitation, right? So for all zeros there is a 1 at D naught, right? So here you can see all zeros, but we have a 1 at D naught, right? So this is another problem. So in order to overcome those two limitations, right? So these are mentioned here: 2 or more inputs high, right? And all inputs 0. So here you can see we have all inputs 0, but 1 at D naught position, right? Right? So what we can do, we can add another output with label V, that is for validation, right? So here we have, you can see that 0 0 0, right? So irrespective of the outputs, if we have validate or V0, right? So we don't care regarding the output, right? So whenever V is 1, right? So you can see we have 1 0 0. So this is V1, right? And here we have don't care at D naught, right? So it means this combination has two different choices. We can have a 0 here or 1 here, right? So here we have two don't care conditions. So it means 2 raised to power 2, 4 different possibilities for this combination, right? So here we have 3 don't care conditions, so 2 raised to power 3, 8 different possibilities for this combination, right? So here you can see row 3, 2 combinations, right? And row 4, because we have 2 don't care conditions, so 2 raised to power 2, 4 combinations. And for this row, final row, row 5, we have 8 different combinations, right? So we have 3 inputs, one for V, that is representing validate, right? So the idea over here is, if we have 2 or more ones high, the one with the highest priority will be considered, right? So this is the solution to those limitations mentioned before, right? So if you talk about the Boolean expression, so we can always have the K map, right? So you can see D naught, D1, D naught, D3, D2, right? And this is for A1, right? And this is for A naught. So we have for A1 D2 plus D3, right? For A naught D3 plus D1 D2 bar. So these are the equations, Boolean equations for A1, A naught and V, right? And this is the circuit diagram, right? For 4 to 2 priority encoder, right? And this is the utilization of an encoder, right? So you can see that here we have different machines, right? And the output from those different machines has to be encoded in order to be fetched to a controller, right? So, and on the basis of those encoded output, an action has to be taken, right? So this is the application of an encoder, right? So we have applied it on a monitoring unit. And now let's move to the demultiplexer. So as we have decoder, right, and then we talked about encoder, so they are opposites. So similarly, a multiplexer, right, that select one of the inputs, right, and launch the data from that input to the output, right? So one into many into one, right? So a demultiplexer functions on the opposite basis, right? So it distribute the data from one line to the different output lines. So you can see the functionality over here. So this is a typical multiplexer, right? So this is demultiplexer. So here you can see that we have one line, right? So this is the this is very common scenario when we have to launch data from different input lines onto a single channel or single line, and then we have to distribute the data at the destination, right? So this is a single channel between two big cities, right? You can say, and then these are the different inputs or different lines that has to be multiplexed onto this single channel, and ultimately on the destination side you want to distribute that data to those different lines. So remember that we must have a synchronization, right? So the time slot that has been given here should be the same as the time slot while we are distributing the data, right? So this is the functionality of a demultiplexer, right? So you can say or see it performs the opposite operation of a multiplexer, right? So you can see if we have one input, right, and here we have 1 into 2 demultiplexer. This is the enable, this is the select, right? So when S is 0, D0 will be selected. When S is 1, D1 will be selected, right? So this is the block diagram of a demultiplexer, right? So here we have 1 into 4 demultiplexer. So in order to control 4 output lines, we need 2 control switches, S0, S1. So you can see we have whenever we have S0, S1, 0, 0, right? D0 will be selected, 0, 1, 1 will be selected, right? 0, 1, 0, D2 will be selected, right? And 1, 1, D3 will be selected. You can see that D0 is equal to E, right? 0, 0, right? D1 is equal to E, right? And then we have whenever we have 1, 0, D2 will be selected and D3 will be selected, right? So this is the circuit diagram, right? 1 into 4 demultiplexer, right? And that's all for today's lecture. So today we have finished multiplexers, then we talk about decoders, their applications, and after decoders we discussed encoders, their applications, and finally we talk about multiplexers. So that's all for today's lecture, right? मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम.